Hello world, it's Craig. I've been fielding a few questions about this 8085 STD board that I started this spring, so this video is going to be an update on that project. I've been spending some time getting to know this little 8085 single board computer. It's for the STD Bus, and so far I really like its features and design. I especially like the memory mapping and the freedom to put the ZIF socket, or these three memory sockets, anywhere that I want in memory. So when I'm writing the boot code, I can have it down at 0 like it is now, or when I'm writing code for the upper memory, I can put it up where I eventually plan to put that code in the EPROM memory card. And since I've been moving the memory mapping around in this board and constantly reconfiguring it during testing, I wish I had put in the little SIP switches here so I didn't have to redo the wire wrap every time. But I'm reconfiguring it less and less every now, and the pins in this little wire wrap is a lot cheaper than the SIP switches. So when you build the board, there's the choice of the $6 SIP switches or 75-cent breakable header that you can just wire wrap to. One thing that I would do different if I do put these headers in my next board, I would do something to make pin 1 different. I would either put a gold-plated pin in for that one, or I would make it taller or something, because until I get a chance to space these out a little bit different, it's a pain to have to keep counting and finding out which is pin 1 or looking on the back of the board for the square pad. But at any rate, you may remember that this board can have 2 completely independent memory maps, and which map it uses is controlled by a bit on its output port. So I've tested that the memory swap works as it was designed, so I can swap back and forth between 2 different memories by swapping one of the bits on this output port. And I've tried this for maybe a half a dozen or 10 different configurations of memory. Right now I've just got a RAM in here and an EPROM. Now when the board gets reset to 0, it goes to the default mapping, and then flipping that little bit flips it back and forth between the default and the alternate map. Obviously it was needed for CPM, but I generally prefer bare metal, so it was a fun exercise. But other than the initial testing, I really don't have a need to do a lot of memory swapping on this board. I will use memory paging and segmented memory, but in terms of having the 2 different mappings, if I don't run CPM on this, that's probably not going to be a high priority. Now, one thing that I have already added to my change request is I've got all of these bits on the output port that aren't really doing anything. One of them runs the speaker and one of them is for the memory map. So one thing I did put in my change request is to use a couple of the output bits of that onboard port to control the extended memory and maybe the extended port control line. So on the STD bus, there's one line that right now on this card is just tied low, and that's to use the extended memory. So you can tell other cards in the system whether to be enabled or disabled by looking at that extended memory bit or the signal on the backplane. There's also one for the extended I/O, but I'm much less likely to need that much I/O on my little systems. So I have put in the change request to take one of these bits that's just running an LED now and use that to control the extended memory signal. So probably as well, I'll just leave it connected to the LED. Now most of the STD cards that I have can utilize that bit, and I've been testing it with some Prolog cards. Since they can utilize that bit, we might as well allow this board to control them. And that memory paging is, it's especially useful for ROM cards, but it sometimes can be useful on RAM cards as well. Now, in addition to the extended memory, that control signal that's on the back plane, some of these cards are also designed to use segmented memory. So you can see they may have a connector here on this end, and that's to use segmented memory or, paged memory. So you can page this entire card in and out. So you can have multiple ones of this card, and then by using an external signal from an I/O port, you can segment this or page this card in and out. So I think I'll use some of these other outputs on this port and bring a header up here somewhere on this edge, on the ejector edge, so that I can then patch this over to cards that use segmented memory. And if you look in the documentation for the Prologs, that's basically what was intended to do. You run just a little twisted pair from each of these cards over to an I/O port. So rather than having another I/O card, if I had a connector out here that I could bring some of those to, I could then also use this card for segmented memory. So those are 2 things that I have on my to-do list or my change list. After I'm done exploring this card, I think I'll do a couple of patches on it, and I'll connect one of these bits to that expanded memory, as I suggested, and I think I'll also use a couple more of those bits to kind of jerry-rig in and make a segmented memory control. Now, as a note of interest on modifying my boards, you may notice that on some of my schematics, there's trace cut points. So typically on a board, I will use either jumpers like this, or I'll allow for the use of SIP switches or dip switches to allow frequently changed or reconfigured things to be simple so that you don't have to get the soldering iron out. Then the next step above that is I'll use solder bridges on the back for things that are infrequently changed, or things that just need configured every once in a while, maybe only once when you build the board. And then if I have unused inputs, I will put in trace cuts for patching or tying unused gates down and so forth, so that you don't have to find the trace. Somewhere on this there'll be a place for a trace cut. So you can look on the schematic and you can see that I have trace cuts called out on the schematic. And if we look at a board here in a microscope, you can see I've got little trace cuts here. Here's trace cut 7, 10, and 11. So this is just a little 10 mil patch where the solder mask is exposed. And the intention is that you can come here and you can cut the trace if you want to modify that signal. So here for these traces, 7, 10, and 11, you can see on the schematic, these are just some inputs to this 74 LS244 that are being tied to ground. So if we decide later we want to use one of those for something else, we can cut that trace, come back in here, and then patch a wire to that pin. So to cut that trace, you can use a utility knife, a moto tool, or whatever your favorite means is. That's a fairly small trace. 10 mil is pretty small. Here's the tip of the pencil. Of course, it's not very sharp, but this is a fairly small trace. So you're going to be using a little microscope and some care when you want to cut that trace. But nonetheless, it's on the back of the board, so you can get to it even after the board's been built. On this board, I'm just going to trace cut 2 here on the extended memory control line. TC2 is currently tying that pin low, so I'll cut TC2 and then patch it over to one of the output bits. Well, back to this board. The first testing I did was just with the board by itself, without a backplane. I had the 8155 IO RAM, I had a 6264 RAM, and then right now I've got a 27256 EPROM. And I tested this with, as I said, about a half a dozen different memory configurations. But right now I'm just using the 27256, even though I'm not using all of it, just because that's what I had. Then after testing the memory map swap and other things on the board, I started testing it in this STD backplane with other cards. As you can see, I have it running with a Prolog 7303 keypad display. And then inside there's a couple of Prolog 7702A byte-wide 16K memory cards. So I'm still using this 256 EPROM, but I've reconfigured the map so only the low 16K is being selected to make room for these other boards. And you could, of course, leave holes anywhere in memory. The card doesn't care about your motive or intentions. It only selects those blocks that are jumpered in the map. So the same EPROM in one of these sockets could wrap around a little memory card in STD Bus if you felt the need. But this is my current mapping. I've got M3, which is that ZIF. I've got it from 0 to 3 FFF. The rest of the EPROM is just going fallow. I then have 2 of the 7702A boards, one coterminous with M3 and going up to 7 FFF, and the next up to BFFF. And then M1, this guy right there, which is a 6264, and that's going from C0s up to DFFF. So I have a nice contiguous block of RAM from 4000 through E0FF, which is the top of the 8155, because after this M1 at DFFF, the next is the 8155 that kicks in, and it has its 256 bytes of RAM. So that's a nice contiguous block of RAM. So on this board, you need to select 2 1K blocks for the 8155. So this RAM in the 8155 loops back and is reselected on E100 to E1FF. But it's the same RAM that you're talking to, so don't get fooled to thinking that you have anything other than fold back on that RAM. Now, as a side note, if you're looking for a good general purpose memory card These Prolog 7702As are 16K cards. They're a nice universal card, and they seem to be widely available. They're designed as two memory banks. So you've got a bank here and a bank there, and they can be configured differently. You can have a combination of EPROMS or RAM on these cards. So this one is configured completely as RAM in both banks, but you could have one bank of EPROMS and one bank of RAMs. These would all be 2K EPROMs. And this is nice. This is the 7702A. The 7702, the one before this, was just for EPROMs, but the 7702A was upgraded to have these universal memory sites. If you find these, they're a nice addition to your STD system. I'm planning on having on the CPU card 16K of ROM and 8K of RAM. And then I'll have one of these 16K with RAM in it, just like this one is configured, or the ones that are in it. And then a couple of these with EPROMs that I'll page swap. So in terms of 8K blocks, that's going to be 1, 2, 3, 4, 5 for the RAM, and then 6, 7 for the EPROMs that I'll be page swapping. And then the subdivided 1K blocks with 8155 occupies the last 8K block on this card. So that's going to be my 64K of memory in this little system. So this is where I am in testing. In addition to the 7702A, this card, oops, that's the 7702. In addition to this card, which is the 7702A, now keep in mind, again, the 7702A is the upgraded version that has universal sockets with RAM or ROM. This is the original 7702 that can only have EPROMs. But they're significantly different. You can just tell by looking at them that they're different. So even if the seller doesn't know what they have, you can tell what you're buying. This is the one that's only EPROMs. This is the one that's universal. So that was the 7702. There's also the 7703 and the 7706, with are both up to 16K of battery backed up RAM. So it has a little battery backup here. So this is the 7703 and the 7706. We also checked it with those. Then there's the 7704. 7704 is 32K of RAM or ROM, universal sites again. And then finally, I've tested it with the 7705A, which is the replacement for the 7705, and it holds up to 32K of 2732 EPROMs. But so the number can get confusing. Make sure you know that you're buying what you want. The 7705 and the 7705A, even if it was upgraded with that A suffix, it can only have EPROMs. So it's not like the 7702A, which has universal sites. If you want universal sites, you've got to go for the 7702A or the 7704. 7705 doesn't have universal sites. So anyway, if you're using any of those memory cards, then you should be golden, because I've tested this board with these cards and they seem to be working just fine. So that allowed me to test the memory access and the back plane access with the address and the data and everything in memory mapping. Then to test the I/O mapping, as I mentioned, and you can see here, I've got the Prolog 7303 keypad and the display board, and I mentioned this in an earlier video. It's really a fun little card. It uses the same intelligent MOSTEC display. So this is the DL1416. That's the same one, or the same family anyway, as the DL2416 that we used on this little F8 board. So you can see that physically they're bigger. The display is about the same size. The actual globe part of the display is about the same size. Physically quite a bit bigger, but it's an intelligent display. You just write ASCII characters to it, just like we did in the F8 board. So this one that's in the system was set up as ports 0 and 1 when I got it, and I haven't had any reason to change those port addresses. On this, the 8155 port is way up in the E something, I think, with my map. Where was my map? Yeah, the way I have it set up, the Prolog 7303's got its data at 0, its control at 1, and the onboard port is at FC, and the 8155 port is going to be in the E0. It's going to start at E0. So this is a nice, simple, fun board to use. You just need to write the ASCII character to the data port, and then the position where you want that character to go to the control port, and then you write the strobe for the displays manually. So it takes 3 writes to actually send something to display, send a character out to display, but that's not a big deal. And in this confidence test that I've got running, it just banners a message until a key is pressed, and then it will give you the address of that key. And when the input, you just scan those ports, you set one of the rows, and then you scan the columns to see which key is pressed. So this is going to be 0, 2, 4, and then I think 1, 0 is, 1, 0 is this button over here, and then 2, 0 is that one up there. And then this is 0, 1 for the second column, 2, 4, 6, or 8. And then I think over here, yep, and then up there. So all of these are just scanned except for this one up in the top right corner, which is the reset button. One thing that's nice on this board, since you have full control of the scan, it's really simple to interface. And, for example, if you just want to check for any key press, you can enable all the columns and then just test the input column byte for non-zero, and that'll tell you if a key is pressed. And then it's got the 2 rocker switches, and these are just fixed on the bit 7 and bit 6 on that port. So you've got 2 rocker switches, and all of these are being scanned. So if you happen across one of these 7303 keypad displays, I think it's worth getting. It's really fun if you've got an STD system, unless the seller has it, tremendously overpriced, of course. As I mentioned, there's a couple of things I want to revise in this design, and there's likely to be some undiscovered bugs left on this board. But, that said, I think it's far enough to be useful so that others can start to, play with this board, and, maybe they can help find some issues. But overall, things are looking good, so I'm going to get into the documentation, the BOM and so forth, and then go ahead and release this design for build. Even though it's not perfect, it's very functional. I haven't found any problems with it. I found things that I want to change, but I haven't found any problems with the board itself. So keep in mind there's going to be a revision someday, and some of them could be, I don't know if it's fairly major or not, but one thing that I'm going to do is on my change list is to flip the order of the pins on this 8155 output port. So whether or not you want to build this board or wait for the next revision, that's up to you. Now, things that I have not tested on this board. I have not tested the bus request to put the 8085 into a hold to do DMA or anything like that. So I haven't tested the bus request feature on this. I haven't tested jamming data onto the bus via the interrupt request and acknowledge. And so there could be a little bit of a fault somewhere in the logic that allows you to jam an instruction on the bus. I haven't tested that. I guess I haven't actually tested the timer in this 8155. Let's see what else. I've really only tested this with the 6264 RAM. Then I've tested it with 2732s, 2764s, 2756 EPROMS. So there's many gaps in terms, to fill in as far as the possible memory configurations. I haven't tested this with a single 27512 and M3. And note that only M3 can use A15, so only M3 is the one that can use a 27512. And I haven't tested this with any double EPROMs. So like I said, there's still plenty of room for hardware bugs to be discovered in this. And, kind of as usual, I'm going to give away the rest of the boards I have from this first run. I've already given a couple of them away. And the rest of them I'll give away on a first-come, first-served basis to those that are willing to pay for the shipping. So if you want a board, just add yourself to the queue by leaving a comment indicating as such below. And then email me using the contact information on the project website that I'll have down in the description. You can give me your address and arrange to PayPal me the shipping cost, or you can just send me a shipping label for that matter, and I'll put that link below to contact me. So, as always, rather than getting boards from me, I encourage people to submit the job to their local favorite board house and then share the extra boards with anybody you think they may be interested. That's probably it for this board. As I come across additional items that are mistakes, version changes, and so forth, I'm just going to put them in the documentation that's on the project page. I've already got that user's manual started. It has the BOM in it, the schematics, and so forth. I'll also put up the confidence test that I'm running on that project page so you can reconfigure the memory map the way that you're using it and just reassemble that source code for your mapping. Now that confidence test does not require any cards in the STD backplane. So that confidence test will allow you to just run with the CPU card by itself. And for that, it does, actually it doesn't even need the 6264 RAM. It uses, generally the way I have it assembled is you can use either one of these for the stack, the 8155 or the 6264. But I think that the way that it's assembled now, it only uses the 8155. So it does need the 8155 the way it's assembled, but you can swap that out if you want to just use the 6264 rather than the 8155. With the confidence test, I'm giving you the source code as a starting point, so then you can add your own code, you can reconfigure it, you can reassemble and tinker to your heart's delight. As always, if you find anything that's wrong, unclear, or simply missing from the documentation for this card, let me know. Okay, if there's any major events, I will let you know, but probably that's going to be the last video on this card. I'll move on to some of the other projects. So until then, thanks for watching. Talk with you later. Bye-bye.